So this is our frequency counter from before, and I have it set with that test signal of about 100 hertz, and it like fluctuates a little bit just because of all the breadboarding part of it. But I've adjusted the circuit now so that it could be a period counter. And now I'm going to explain how it works. I've added third board here, and this is the board with the T flip-flop. So that T flip-flop that I had on the breadboard in a previous video is now basically going to be the gating signal, the sole gating signal, and not this 0.5 hertz clock. So the problem with this anemometer is that it's never going to spin at a really high frequency. And so when it doesn't spin at a high frequency, the reading that I would get on a frequency counter in hertz is going to be maximum 1 or 2 or 3, unless there's gale force winds. So in order to adjust for the frequency and make it higher resolution, I'm building a reciprocal frequency counter. So basically, the first step in building a reciprocal frequency counter is to, rather than measure the rotations per second with the frequency and then do the math afterward, we're going to measure the period. So we have a 100 hertz signal, which is the test signal right there, and it's reading about 100 hertz and 98, 99. So it's close enough. I can calibrate it using this potentiometer that I've added to the circuit right there to make it a 100 hertz signal. But every time I come close to it, whatever current is in me screws everything up. So I'm going to try to make it work here in its current iteration. There we go. We're getting 102 hertz right now. And it's fluctuating just based on the capacitance in that little board. But in any case, what I've added to this circuit is a switch. So the switch can switch from this middle board, which is the gating, the half hertz gating signal, to this other board, which is our T flip-flop using transistors. I've shown the circuit before. That T flip-flop is controlled by an input using this yellow wire from the anemometer. So basically the anemometer, the way it works is it has a Hall sensor, which is right there. And that Hall sensor, it's a Hall switch. It's an A3144. What it does is it starts high, and every time there's a magnet sensed, and the magnet is underneath this guy right here, it sends a low signal. And so what I've done with this circuit is using a transistor, I created a NOT gate, an inverter basically. And so that signal is now going to be a single positive pulse that comes out of the Hall sensor. And so you could see it with that little white light that comes on every time there's the magnet is sensed there. And anytime that light is sensed, that signal from the Hall sensor basically goes through this wire, and right now I have it just connected with the breadboard, but then it connects to this T flip-flop. So every time it goes on, it turns the T flip-flop on and off based on the rotation. Okay, in this way, using that T flip-flop, if I start here where it first triggers it on, and then it rotates an entire rotation, and then it turns it off, that is the period of the rotation. So if that's the period of rotation, I have an output going from that flip-flop through this yellow wire to this little switch, And when I flip the switch to that signal, this gating signal no longer applies. And rather, the gating signal is applied to the period. It's the same 100 hertz input signal, but instead of this light may be flashing, but it's not doing anything. And so right now it's reading 0, and I have a decimal now that's programmed in there through this switch too. So if it's a 100 hertz input signal and it's being gated by this flip-flop, every time the flip-flop is on for whatever period of time it takes to rotate, make one complete rotation, it will give us the number of pulses from a 100 hertz signal and in this display. So that number of pulses is basically, since it's a 100 hertz signal, it's basically hundredths of a second. And so what happens is when I rotate this now, it measures the period. 0.56, 0.65, 0.55, and this is the number of seconds basically that it takes to rotate. I'm rotating this about, you can see the light in the background, about 2 hertz or so. Just manually spinning it. If I try to spin it faster, I get shorter periods. So the plan here is now to incorporate this 100 hertz signal, now that I've stopped rotating this, into, and you can see as it rotates really slowly, it gives you a much longer period. Here's 3-second period measured. It keeps going, 1.65. So in any case, the plan with this is how you convert the period to frequency. So the way, if I have 100 hundredths of a second measured here, the way to do the math for this is basically, if I was to divide 6,000, the number 6,000, by the value, the number of pulses here, in this case, for instance, 116, well, let's say if it's 100, 100 will correspond to exactly 1 second for a period of rotation. So let's say that value is 100. I'm going to try to make it 100 here, so 1.04, right? So if this is 1 second, if I take 104, and I put that in the denominator, and in the numerator I have 6,000, so 6,000 divided by 100 will equal 60. So that's equivalent to 1 hertz or 60 rotations per minute. So the next step in designing this is basically, rather than doing this count and displaying it here, what I'm going to have is I'm going to load this into a presettable down counter. And then I'm going to have a separate clock running at a fast speed, probably another 555 timer, and basically counting down from 6,000. And every time that down counter reaches 0, it's going to send out a pulse that's going to go to a separate counter, and that is going to give us rotations per minute. And then from there, we can do a frequency multiplication or frequency division, whatever needs to be done to turn that into knots or miles per hour, with fudge factoring and all that included. So this is the latest ongoings with this project, and this is a little bit of an explanation. You can see that T flip-flop is currently off, and as I rotate this, that triggers the T flip-flop to be on. So right now it's actively counting hundredths of a second, and if I make this go off, it's 8.92 seconds from the last period. That was 2.4 seconds, 1.37 seconds, 1.02, and as I keep spinning it faster, that period number goes down because this is a number, it's counting time rather than frequency. And the flip-flop provides the gating. Now this just is going to continue. The blue light here is the 1 second frequency counter that I built before. It's all just basically included in one big circuit here. But if I switch it back to that, it's going to be counting that straight 1 hertz frequency signal that's coming from there, 100 hertz frequency signal that's coming from there. And so I would say this is working fairly well. Now I have enough to basically start doing the reciprocal frequency math using some counters. Anyway, thanks for watching. I'll get to the schematic if somebody wants it. Have a good one.